Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 14, Part 1, Anova for completely randomized designs. So one other thing that you might want to do after you do an overall F test to see if there's a difference in the treatments is you might want to say, but specifically, what's the difference between these specific two treatments? So what you could do is you could create a 95% confidence interval for the difference in those two treatments. This is the formula that we're going to use, y bar I minus y bar j. So that's the sample mean for treatment I and the sample mean for treatment J, plus or minus T alpha over 2 S epsilon times the square root of 2 over N. And in this case, this is assuming that we have equal sample sizes in each of those groups. So we're going to use this Fisher's LSD procedure. And our goal essentially, once again, is to evaluate the difference in treatment mean I and treatment mean J for a K-factor treatment structure in a completely randomized design. All right, so we have our strawberry example where we have 4 groups and each group has 8 observations. We have the rating of the discoloration for each of the bags of strawberries. We've created a data set, and what we can do from last time is we said, oh, we could rename the YIJ to be data dollar discoloration. We could rename the groups so that the group is recognized as a factor. So after doing this and we take our summary of data, you can see that our original grouping was a quantitative variable because it's giving you the 5-number summary and the mean. Once we create it into a factor, you see that as a categorical variable where there's just group 1, 2, 3, 4, and there's 8 observations within each factor. So that's what we've done by using this factor command in R. We can find the group means by using the tapply function, where we say for data dollar discoloration, give me the mean for each group. And by doing this, we find the group means to be 8.3125, 6.4375, 4, and 2.5. Since the ratings give you the amount of discoloration on a scale of 1 to 10, where the low ratings means little discoloration, group 4 has the least amount of discoloration for that particular preservative, whereas group 1 was our control group, meaning that those strawberries received no preservatives. We can fit a completely randomized model using the LM function in R, where we say let YIJ follow factor group. We identify our data set to be data, and we ask for the summary. Here are the coefficients, and this gives us the overall F test. Okay. Similarly, we could have said discoloration follows group, and since that capitalized group was already a factor, we don't have to write factor of group. We can do the Anova of fit 1, and we can get the summary as well. Now, when we're doing this, this overall F test was significant. So that means that we were saying, hey, there are a difference in these 4 treatments. But you might ask later, what about the difference between specifically group 3 versus group 1? Is there a difference for that preservative? Or is there a difference for any subset of comparing 2 treatments? So what we're going to do here is we're going to go one step further, and we're going to continue to get all the pieces that we need to be able to make this confidence interval. So real quick, we could say, okay, what are the names of fit.cr? What are the things we can pull off? You know, you can pull off the coefficients, you can pull off the residuals, you can pull off some degrees of freedom and the fitted values, right? Similarly, everything in R is an object. So we could say, what are the names of summary of fit.cr? And one of those is sigma. And that sigma is going to be related to that S epsilon, right? We know that S epsilon squared is equal to the mean squared error. So if we look at the Anova table for fit.cr, we see that the mean squared error is 0.953. And remember, S epsilon is approximately equal to the square root of MSE, or I should just say equal, that's fine. S epsilon is equal to the square root of MSE. So we're just going to double check, is the summary of fit CR $sigma squared, does it equal the MSE? And it does. So that is fantastic, because that means we can pull off that sigma and have an estimate of S epsilon. Okay, similarly, we could have said, what are the names of the Anova of fit.cr? And we see that one of the names is mean square. So when we say Anova fit.cr $mean square, we see that this second piece here, that's the mean squared error. So we could have also pulled off the mean squared error using that value. So either one of these will give us the mean squared error. So our next step is going to be to define S epsilon. And we define that as the summary of fit CR $sigma. We could have also said it's the square root of Anova of fit.cr $quotes mean square quotes and square bracket 2, and that would have been okay, but this is just like a lot more typing than this really simple way of doing it. So that's why I did it the first way. So S epsilon is 0.976. You can check in your calculator that that's the square root of 0.953. Now, large N is our sample size. We had 4 groups, each with 8 bags of strawberries. So our sample size should be 32. And when we look at the length of data $discoloration, that gives us our 32. We had 4 treatments, and we can do the length of the unique data $group. So if you think about it, we had 4 groups, and even though in our data set they were repeated 8 times each, by saying what are the unique groups, then I'm just going to have 1, 2, 3, and 4. So T is 4. I'm defining N to be 8 because each of those were repeated 8 times. My alpha level is 0.05 because I'm trying to find a 95% confidence interval. I need the critical value for T, so I use QT because that says if I give you the area under the curve, what is the value of T associated with that area? So I'm putting alpha over 2 in each tail because we're doing a confidence interval, right? If 95% of this is in the middle, 0.025 is on each side. That's alpha over 2 on each side, and 1 minus alpha in the middle. Okay, I'm saying lower tail equals false because I want this positive value for T crit, and we get that value to be 2.048. All right. We need to get our y bar I minus our y bar j. So we had already defined those group means. So I'm doing group means 3 minus group means 1 because that's our sample mean for group 3 and our sample mean for group 1. And I'm defining that to be the difference in means 3 versus 1. So to create the confidence interval, we have the formula here at the top. We take that difference in means minus our T critical times S epsilon times square root of 2 over N. The upper value is the difference in means plus T critical times S epsilon times square root of 2 over N. And I finally obtain my confidence interval is negative 5.312 to negative 3.312. So let's interpret that in context of the problem. We are 95% confident that the true difference in the mean discoloration of the strawberries is between negative 5.31 and negative 3.31 points, right? Remember, this is on a 10-point scale. Okay, now what that means in general is that the preservative 3, right? Preservative 3 has less discoloration than preservative 1, which is our control group. Now we know that because our 95% confidence interval does not include 0, right? If the confidence interval included 0, then we would say that there's a chance that there's no difference in the discoloration. But since this confidence interval is between -5 and -3, that means that preservative 3 on average had 3 to 5 points less discoloration compared to preservative 1. So I hope you learned something in this video, and I'll see you next time.